Okay, so we were talking about syringes and stuff like that. Let's talk a little bit more. Let's do some more examples of scales and stuff like that on our syringes. So I'm going to label this one here. So looking at this syringe, I want you guys to take a minute and I want you to tell me what each division on that syringe represents. How many milliliters is each division? So our big thing is look between consecutive labeled marks. So from 1 to 2, of course, 2 minus 1 is 1 milliliter. Then count the number of spaces between them. There's 1, 2, 3, 4, 5. Obviously, we can extrapolate that's 10 spaces. 1 milliliter divided by 10 is 0.1 milliliters per space. With that in mind, let's say we need to load 3.4 milliliters. Tell me where to stop. Right about there. Perfect. We know that it's 0.1 milliliter per mark. We start at the 3. We count up 3.1, 0.2, 0.3, 0.4. Beautiful. First of all, would this syringe be appropriate if I was supposed to give a dosage of 0.8 milliliters? That's kind of a gray area on this one. That's a little under halfway, but it wouldn't be horrible. But if I had the option between that syringe and this syringe, which one would be better? The bottom one. Because 0.8, this being a capacity of 2 milliliters, or a little over 2 milliliters, and this one of a little over 1 milliliter, obviously 0.8 is closer to the 1 milliliter. Let's go through each of these and figure out what each division represents. So up here, from 1 to 2, 2 minus 1 is going to be 1 milliliter. The number of divisions, well, we've already counted there's 5 in that set. So 5, 10, 15, 20. Dividing by 20 gives us 0.05 milliliters per division. Now, if we wanted to measure out 0.8 in there, which would not be a great idea in this one, we would have to count backwards from the 1. Because remember, we said that the bottom end down here isn't necessarily an exact starting point. The 0 line usually isn't shown. So from 1, this would be 0.95, 0.9, 0.85, and 0.8 would be right there. This one down here, finding the scale is a little more difficult. We'd probably would have to have more labels on it like this. Oops, what did I do wrong? That label, we probably just have to do that apparently. This one we would have to calculate the amount per space again, but it would be 1 minus 0.5 is going to be 0.5 milliliters. It would still be 5, 10, 15, 20 spaces, which makes each space 0.025 milliliters, which makes this one a little bit harder to deal with. If I wanted to find 8 or 0.8 milliliters on this syringe, what I would do, rather than trying to count down by 0.025 milliliters per marking, I would say times 4, every 4 markings is 0.1 milliliters. Does that make sense? You could also do times 5 or times 2, and every 2 markings would be 0.05 milliliters. It would be easier to count down by. So what that means is if this is 1 milliliter here, I go 1, 2, 3, 4. That's going to be 0.9. That's 0.1 milliliters. 1, 2, 3, 4. There is my 0.8. Make sense? That's kind of a poor scale on that one. So let's label this one. So if this one is filled to there, how much is in it? I'll just mark it here. That is actually one short of coming up there. Once again, we have to go between marks. Since we're right up in here, I'll just use the 0.3 and the 0.4. Subtracting, that's 0.1 milliliter in between. How many divisions are in between those? 10. That's 0.01 milliliters per division. So I either go from the 0.3, 0.31, 2, 3, 4, 5, 6, 7, 8, 9, so 0.39. But I could have counted backwards from the 0.4 minus subtracting 0.01 would be 0.39 as well. How do you guys feel about syringes? Okay with the scales and stuff? Anybody want to see another example or two? Okay. That's one I don't want to beat to death, because most of you can read a ruler, you can read a syringe. Okay. The next step is we're actually going to start the dosage calculations. To me, the trickiest part about the dosage calculations is there are three methods. The method that the book pushes is also the method that the dosage calculation book you get pushes if you're in the ADN program. And to me is also the most difficult method to use. The reason that the books push it is because it's a very cookie cutter. It's a formula. You just plug in the numbers in the right spot and crank out an answer. You don't have to think about it at all. The problem is the formula only works in certain cases, and there's other formulas you have to use in other cases, and it gets messy. I like to use basic math processes where you can just use the same process for any problem and it'll get you to the answer. So anyway, we'll start out with that method, which is the formula. The formula is D over H times V equals A, where D is your ordered dose. And A is the administered dose. H is what is referred to as the on-hand dose. What does that mean? Well, what that means is if you, let's say the ordered dose is 800 milligrams of medication. Let's say it's Tylenol or whatever. And you have 200 milligram tablets. The on-hand dose is the 200 milligrams. That's how big the tablets are. V is the vehicle. The vehicle is what carries the dose from the bottle or the vial into the patient. That's one of the trickier ones to understand until you see some examples. So let's just do that. Let's do that example. We have an order for 800 milligrams of a medication. We have a bottle that is labeled 200 milligrams per tablet. So setting up our dosage calculation formula, the ordered dose is the 800 milligrams. The H, the on-hand dose, is the size of the tablets. That's 200 milligrams. Very important note here, the units of the ordered dose and the on-hand dose must be the same. So both of these are in milligrams, so we're okay. The vehicle has to somehow be related to the on-hand dose. In other words, it has to be what actually contains that dose and is going to carry it to the patient. In this case, the vehicle is a tablet. So really what this is saying is 200 milligrams for every one tablet. So now we go ahead and we divide. 800 milligrams divided by 200 milligrams is 4 times 1 tablet is 4 tablets. To me, that's a really complicated way to go through a simple calculation. Let's look at another example. Say our order is for 80 milligrams. And we look on the bottle or the vial, and it is labeled as 4 milligrams per 5 milliliters is the concentration. So to set this up, our ordered dose is 80 milligrams. Our on-hand dose is 4 milligrams. Has to be the same units as the ordered dose. It has to be milligrams there. Now remember, we said the vehicle has to be related to this on-hand dose. So if we look at this relationship, the 4 milligrams was carried in 5 milliliters of the fluid. So what we have here is the milligrams cancel out again. 80 divided by 4 is 20 times 5 milliliters is 100 milliliters. Any questions? That formula works nice. It's a nice cookie cutter little formula. If you have simple problems, you can plug them in, crank them out. To me, that whole idea of a vehicle is quite confusing, but once you see it, it's not horrible. But to me, the other methods are better. In fact, we're going to do the method that I prefer last, as I'll show you the other methods that the book does touch on. So again, the dosage calculation formula is pretty much cookie cutter. You just plug the numbers in to where they belong. The second method I'm going to show you is a proportion method. The proportion method, we take the desired dose, or the dose that we want to deliver to the patient, and we find it from the label on the bottle. So we take the label on the bottle, and we are going to compare it to the administered dose and the ordered dose. Let me show you what I mean. And I put these over here not in any particular order because it depends on how things are set up on the label. So anyway, let's say that we have an order for 250 milligrams of medication. On the bottle or on the vial, the label says 50 milligrams in 20 milliliters. So I'm going to take the label on the bottle, 50 milligrams in 20 milliliters, and I'm going to set it up as a ratio. So being a proportion, we're going to set up, and this is not a ratio, it's a rate because the units aren't the same. Being a proportion, we're going to set it up with another rate on the other side that has to be equal to it. On this other side, however, the units must be the same. There's milligrams here, must be milligrams here. Milliliters here, must be milliliters here. So now looking up, we've used the 50 and the 20. We still have the 250 milligrams from our ordered dosage. That has to go on top. Now, we cross multiply and divide. 20 times 250 divided by 50 is 100 milliliters. So there's 100 milliliters of medication that needs to be delivered to the patient. Let's say we have an order for 450 milligrams of medication. Label on the bottle says 150 milligrams in 2 milliliters. Where are we going to start? The label on the bottle. 150 milligrams over 2 milliliters. Then what? Perfect. Since the 450 is milligrams, it has to go on top with the other milligrams. And now, since this is a proportion, we cross multiply and divide. 2 times 450 divided by 150 is 6. That hurts. That'll be milliliters. The proportion method to me is a lot better than the dosage calculation formula because you don't have to memorize the formula. You're just putting together relationships. You have the label on the bottle. You know, these units have to match up. You don't have to identify a vehicle or on-hand dose, or you even need to really know the vocabulary. You just have to match things up. The weakness of the proportion method is if you have a complex problem, you have to use the proportion over and over again. Now, there are going to be problems where the proportion method is a lot better to use, where let's say you have a label on the bottle that says you'll administer 2 milliliters for every 25 kilograms of patient's weight or mass. And you have a patient that comes in that weighs 80 kilograms. Now the proportion method is actually the best way to do it, where now you can cross multiply and divide. 2 times 180 divided by 25 is going to be 6.4 milliliters. But like I said, if you have multiple step problems where you have to go through more than one conversion, this is not the cleanest way to do it. What I think is the cleanest way to do any dosage calculation problem, something we discussed a couple weeks ago, dimensional analysis. What dimensional analysis does is we take the ordered dose and we take it through some unit conversions. To get to what's going to be administered to the patient. The thing I like the most about dimensional analysis is you don't need to really know anything about the medications you're dealing with. It's all set up by the units. Let me show you what I mean. Let's go back to our first example. Ordered 800 milligrams of a medication. On the bottle, there's 200 milligram tablets. Well, first of all, we already kind of made a change on this when we did the formula. This is 200 milligrams per tablet, is the way that's interpreted, even though it says just 200 milligram tablets. But anyway, the way the dimensional analysis would work on this is we take the doctor's order, 800 milligrams. We're going to turn it into a fraction by just putting it over 1. Now, let's say that this were an IV or something like that, where it's ordered 800 milligrams per hour or something like that, well then, you know, there should be 1 hour on bottom or something. We want to figure out what to give to our patient. So we're going to get rid of the milligrams. And since what we're going to give to the patient is tablets, we're going to put tablets up here. The reason the milligrams went on bottom is now in our fractions, when we multiply, they can be cross-canceled. And now the label is saying 200 milligrams, so 200 milligrams per tablet, so per 1 tablet. And now, 800 times 1 tablet is 800 tablets. 1 times 200 is 200. We divide that out. 800 divided by 200 is 4 tablets. Now you might be looking at that realizing it's pretty much the same calculations we did in the dosage calculation formula, except we didn't have to identify an on-hand dose or a vehicle or anything like that. We just put them over here in whatever spot would make the units cancel out. Let's say we have an order for 1,200 milligrams of medication. On the label of the bottle, it says that it is mixed. 200 milligrams in 50 milliliters. So to figure out what to administer to the patient, we take the orders. 1,200 milligrams, put it over 1. Times. Usually it's easiest to figure out what has to go on bottom in our conversion factor. What has to go down here? Milligrams, the 200. We knew that the milligrams had to go down there so that they can cross cancel out. So then, of course, on top, the 200 milligrams is related to the 50 milliliters, so the 50 milliliters will go on top. So we cancel out the milligrams. 1,200 times 50 milliliters will be, what, 60,000 milliliters? Divided by 200, which will give us 300 milliliters of medication that need to be administered. Now, why did I say that that is a simpler way of going about things than the dosage calculation formula or even the proportion method? Because this doesn't have to stop after just one step. If we were getting into IVs, and this is foreshadowing just a little bit, if we were getting into IVs, trying to do a dosage calculation with that, let's say that we were ordered 500 milligrams per hour. And on the label for the bag, we see that this is mixed 500 milligrams per 20 milliliters. Oh, it's 50, sorry, 50 milligrams per 20 milliliters. You guys have a great weekend. Enjoy your spring break. With a drop factor of 12 drops per milliliter. GTT, of course, is the abbreviation for drops. And we want to know then what to set this at for drops per minute. Now this problem looks pretty complex. With the dosage calculation formula, we would have to use the formula at least twice and then still have to convert our time. With a proportion, it would be the same thing. It'd probably be 3 proportions we would have to go through to solve it. With dimensional analysis, it's just one little string of numbers. So we are ordered 500 milligrams, and this is where we said if there's time in there, that becomes our denominator. So 500 milligrams over 1 hour. We need to somehow get to drops per minute. Well, to get to drops, we need to know milliliters. So we're going to get rid of our milligrams here. And we do have a relationship between milligrams and milliliters. 50 milligrams to 20 milliliters. So cancel out the milligrams. Now if I wanted to, if it's easier, and I often do this, I would multiply this out and reduce it because it's easier for me. But you don't have to. You can just keep going with it right now. We don't want our answer in milliliters, so we want to get rid of milliliters. We have a relationship between milliliters and drops. 12 drops equals 1 milliliter. So now the milliliters have canceled out. Are we where we want to be? We've got drops. That part's good. But we still need to change the hours. Now the hours are on bottom here, which means they're going to have to go on top here to cross cancel out. 1 hour, and we want it changed to minutes. So 1 hour is 60 minutes. So now the hours have canceled out. And what we have for units are drops per minute, which is what we want. So we can go ahead and do 500 times 20 which is 10,000 times 12 is 120,000. Drops. 1 times 50 times 60 minutes is 3,000 minutes. We divide that out. 120,000 divided by 3,000 is 40 drops per minute. We're not going to tackle problems quite that complex quite yet. We will when we come back from spring break. But for right now, I just wanted to show you this dimensional analysis. You can just keep going. Now, if having that whole string together was confusing for you, that's fine. A lot of times the way I would have done this is I would have done the 500 milligrams per hour. And I would have converted with the 50 milligrams per 20 milliliters. And I would have ended up with 200 milliliters there. And then I would have kept going from there. Well, then I would have converted from milliliters into drops. So the 12 drops per milliliter. And would have got 2,400 drops. That's still per hour there. Per hour. And then I would have converted the hours into minutes to get it to 40 drops per minute. So it doesn't have to be done all in one long chain, but the nice thing about it is it can be if you want to get it all done at once. But again, you see, I don't have to think about whether I'm going to multiply or divide or anything like that. The units tell me where to put the numbers because the units have to cancel out and convert over to what, from what I'm ordered to give to what I actually have to give to the patient. I realize I have about 25 minutes left, but these are the type of problems that you just kind of have to do to get good at. Rather than me giving you a bunch of examples, I'm going to have you just start working on some out of the book. The stuff on the concentrations is on page 146, 1 through 17, the odds. On page 153 through 154, that's just going over those abbreviations. So I'll have you look at 1 through 15, not just the odds, I'll have you look at all of those. Just to make sure you have the abbreviations down. Again, I'm not going to make you memorize them, I'm not going to quiz you on them. If you want to just mark that page in the book so you can look them up when you have them on a test, that's fine. Just make sure you understand what they mean and how they apply to the problems that we're doing. And then the dosage calculations, the formula, the proportion, and the dimensional analysis, there are problems on that on page 162 through 163. If you want to look at 1 through 23, the odds there. And then on the Shringes, page 168 to 169, 1 through 19. Again, if you just want to look at the odds, that'll cover Shringes.